Now, may I invite Ms. Peng Wong, Secretary General. So up next, we will have Max, software engineer at Dropbox, to talk about hacking the Dropbox Desktop for fun and profit. Max, please.
Hello, everyone. I want to thank you all for being here. This is going to be hacking the Finder for fun and profit, or how to reverse engineer code and get away with it, essentially. So a bit of an introduction. So my name is Max Bélanger. I'm at Max Bélanger on Twitter, which makes a whole lot of sense. I'm Canadian. I'm a software engineering graduate of the University of Ottawa in Canada. And I joined Dropbox as an intern in 2010, and pretty much never left. So let's talk about Dropbox a little bit. So what exactly is Dropbox? Well, it's many things. We are known most for being this like magic folder that syncs. So if you drop something in one place, it'll appear pretty much everywhere else. It works on your Mac, your Linux, Windows, Android, BlackBerry, iOS devices, and a whole lot more. So basically, we're known for being a safe place for all of your stuff. But it's actually going to be much more than that. Ooh, animations. For instance, we now have a mobile email service called Mailbox, which integrates some pretty interesting effects. Like, for instance, it takes full advantage of essentially iOS's like multi-touch experience to be able to give really just a more polished experience over email. It's more about tasks than about just reading streams of conversations, essentially. But let's do a little history first. So Dropbox was founded in 2007 by Drew Houston and Arash Ferdowsi. That's them up there. They were notably funded by Y Combinator, which is an accelerator program founded by Paul Graham. So they moved from MIT in Boston to San Francisco, and then in 2008, they launched for the first time using a video they posted on Dig. And I don't know if anyone remembers Dig, but Dig used to be fairly popular at one point. And so the video went viral, and that was Dropbox's first sort of media splash. Now, if you fast forward to today, well, our founders have much better photos and clothing. Dropbox has about 600 employees now and multiple offices all over the world. And in terms of users, that's over 200 million active users right now, 1.5 million users per engineer if you think about it, hundreds of petabytes of data, and billions of file syncs every single day. Now, a great metric that we use is like how many engineers would that be for each, or how many people would that be per engineer? And that's like roughly 1.5 million right now. So it's like, welcome to Dropbox. Here's your like 2 million people, which is a little crazy. So what do I do there? Well, over the years, I've done a little bit of everything. So I've worked on the server, the web, the desktop. I tend to focus more on the desktop world now. And my current sort of mission is to create new ways for people to work together. Now, that's kind of ambiguous, slightly deliberately. But the cool thing is, essentially what kind of motivates me out of this is that I still feel that it's too hard for people to use software. Like, software still sucks for most people out there. For instance, if you want to try to share a file from like just your machine to someone else, that's hard. Like, that's just still too hard. And you might think like, oh, I'll use AirDrop, right? Well, AirDrop doesn't actually let you send a file from your Mac laptop to your iOS phone. It only works between laptops and between phones. And to me, that's like ridiculous, right? So that's essentially what motivates me, is the fact that software is still pretty bad for just regular people who aren't developers. So basically, I just want to make software work for people. Now, let's take a look at Dropbox on the desktop. So that's for Windows, Mac, and Linux. It's what makes the magic folder. It's written in Python, so obligatory photo of Guido, who is now a Dropboxer, actually. And it's written mostly in Python, with a little bit of C and C++. So Python is great because it lets us move really fast. Now, the downside, though, is that you need to have a lot of testing to make sure that you validate that you're doing the right things. Now, I could spend a lot of time talking about what an adventure it is to ship desktop software using Python, which is fairly complex. But if you want to hear more about this, or like some of the crazy hacks we had to do to just get that working, feel free to come chat with me after. I'd love to go into that. So one of the latest projects that I worked on is a new sort of Dropbox menu. So before we used to have this like little right-click menu only. And this is like our first step essentially into expanding the UI into something that's more rich and that can actually show a lot more of what essentially is what happening inside people's Dropboxes. So we build this across Mac and Windows, but it's basically just the first step into something that's going to be much more. But let's zoom back a little bit to the Dig video, which included a demo on Mac, and sort of why that, or at least part of the reason why that went viral was that we had icon overlays on Mac, which is still something that's not supported by OS X today. So if you used Dropbox before, you've seen how we add these little green check marks or sync icons over files to let you know what the status is. So we're very often asked how we do it. We're a little less often asked why we did that, but I'll try to answer both of these questions today. So I'll spend some time talking about the tech and how we did it. So if you're a developer, if you want details, this is going to be your chance to see exactly what we did. And then after that, I'll speak a little quickly about what that entails for planning and how you actually build a whole process around using reverse engineered code, which can have a lot of downsides if you're not careful. All right, so let's start with the how. So the first idea was, let's try to use the OS-sanctioned way of doing things. Let's try to use AppleScript. So has anyone here like actually used AppleScript before for anything? You poor thing. It's terrible, isn't it? It's like the worst language ever. It's essentially this like supposed to be like natural language, kind of like IPC that you can say like tell Finder to do this, and then Finder will do it, right? Well, as it turns out, unfortunately, there is no API to do this on Mac. So it wasn't going to be that easy. So what do you do, right? What do you do instead? Well, you get Finder to run your code. That's basically what you do. And there are 3 steps to that. So number 1, you need to get some code to run inside the Finder process without killing it or anything. Second, you need to bootstrap this code into loading more complex code that you've written yourself. And third, you want to use that code to override the way Finder itself is behaving. And there are ways of doing that essentially safely. So I'm going to go with all 3. I'm essentially going to go over all 3 of those steps today. So this diagram is a little. Oh. It's actually clearer than I thought it would be. Cool. Well, basically, there are 3 processes involved. You need an injector, so that's something that will just live long enough to be able to send code to Finder. Then you have the Finder process itself, and then you have the Dropbox process, which will be receiving requests from Finder for information. So let's talk a little bit about Mac OS X, which I think is the best operating system in the world. I'm sorry for the Microsoft delegation here. That's just my personal preference. It's not the view of Dropbox or anything. Let's talk about Darwin. So Darwin is actually the open source core that Mac OS X is built around. So a lot of people don't really know this, but you can actually read a large portion of the OS X source code if you want to. Obviously, this excludes Cocoa and a lot of the core apps, but you can actually get to almost every single low-level component that you want. So Mac is essentially built around Darwin, which is the open source kernel, and that's based around XNU, which is itself based on Mach, which is an interesting microkernel implementation. So in Mach, a process is essentially a task. And so why is this important? Well, because the kernel lets you essentially do typical things like make other tasks or do inter-process communication between tasks. But you get to do a whole lot more. So the process API, as you know it, is usually fairly simple, right? It's how do I do IPC? How do I stop process? How do I wait for a process to end? The Mach API actually goes way further than this. So a task is what Mach considers a process, but it lets you do a whole lot more than what pthreads or ns-threads or the regular APIs would let you do. So basically, if you have a task for a process, you can do anything you want to that process. You can create more memory for that process. You can write code inside of it. You can essentially fully control the process if you want to. Now, obviously, getting a task for a process is privileged. And that's why, if you use Dropbox on a Mac, we ask you for your password, because we need your permission before we start going inside Finder, changing things. But essentially, the way you get a task for a process is by calling task for PID, which is a simple function that you give it the process ID, and then it gives you essentially the pointer to the kernel level structure that lets you control the process. So I'll take a quick look at like an example of the code here. Don't worry too much about most of this code. We'll focus on things as they become important. So first, we find the Finder PID. First, we find where Finder is running by getting its ID. So once we have that, then we call task or PID to get its task. Now at this point, obviously, you should have the user's consent to do this. Otherwise, it just won't work. Following this, we allocate new memory inside the process. What we do is we ask, essentially, the kernel to give more memory to the Finder process, just enough to hold the code that we wrote and a stack to be able to run that code. Once we have that, we create a thread inside the Finder process, and we say, run the code that we just copied. And so once we've done that, Finder can actually run any code that we want. OK, so we can get Finder to run like random assembly code. Isn't that cool, right? The problem, though, is that the problem with writing assembly code is that it sucks. It's like not fun. It's essentially machine code, right? You don't have any of the abstractions you usually get. You don't have linking, right? So you can't use libc. You can't even print things to the console. You have literally nothing. You can do arithmetic. You can like add things and divide them, which is great. But that doesn't really get us where we want to go. So what should the bootstrap process do? What should the code that we inject in Finder do? Well, we want it to load, essentially, something higher level that we've compiled beforehand. So the idea, usually, I mean, this is done for you automatically, right? If you dynamically link against something, it'll try to open the shared library, it'll try to find the symbol, and then call it. What we have to do is do that ourselves. But how do you even find the two functions that do this? So essentially, to do this manually, what you need is dlopen, which lets you open a shared library by name, and dlsym, which lets you find a symbol inside that library. So if we wanted to call hey with printf, for instance, we would have to find libc using dlopen, and then we would have to find printf using dlsym. But how do you even find dlopen and dlsym? It's kind of like a chicken or the egg problem, right? How do you link against the thing that lets you link? So the cool thing is you don't have to. Now, obviously, something's got to give somewhere. So what the kernel does is it puts all of DYLD, which is the dynamic linker, at the same place in memory for every process on the Mac. Basically, it does that through a little DYLD func lookup function, which is essentially just an offset in memory. And how do we know this? Well, we read the XNU source code, because it's open source. So you can actually just see this. So let's take a look at an example. First, we find where the function lookup is. And we just do that by adding a constant. So as it turns out, on Mac 10.9, the constant is like OX 1008. That's where it's always going to be on that version of the kernel. Once you have that, you want to go find dlopen and dlsym. Now these two are essentially the only things we actually really need to link against something. And so what this will do is it'll give us a pointer in memory to where that is for our process. Once we have that, well, we actually call the dlopen that we just got with libc. And then this includes a lot of like really strange like Lisp-like syntax with like parentheses and stuff. But essentially, you want to call dlsym with printf. And then once you have the result of that, you want to call it with hey. Now, that would actually work. You know, without actually doing any of the linking, you end up replicating what the compiler would do for you. OK, so now we can load a dynamic library, right? Or we can load a shared library. What do we do now, right? Like we could write that in any language that we want. We could write it in C++ and see how do we pick what to use. Well, Finder is written in ObjectiveC because it's a Mac application. So if you're an iOS developer, you're going to be pretty familiar with that. So it's written using Cocoa. But what is cool about ObjectiveC is that it has, even though it's a mostly compiled language, it has a runtime, which means it has a program inside your program controlling essentially the execution of every Objective-C program. So what that includes is some pretty cool reflection features. So I don't know if any of you have used Java's reflection features before, but it's very neat. You can essentially inspect, without knowing what an object is, at runtime you can inspect what its type is, you can get a list of all the functions, and then you can also do more powerful things. So one thing the Objective-C runtime lets you do is you can say, I'm going to replace the code for this function at runtime with another function. So what we do here is we swizzle. That's basically called method swizzling, which sounds like nefarious or something. But basically what we do is we find certain functions in Finder that we like, and we replace them with our copies of those functions. And we augment them a little bit so they do a little bit more than they currently do. Now this sounds pretty hacky, right? But that's actually what Objective-C does internally when it's running to implement a lot of its features. So if any of you have used or have built Cocoa applications before, or if you've done iOS development and you used key value observing, you've actually been using this without knowing it. Because some of the magic that is inside the Objective-C language is built using what we're actually going to use. So actually, let me sort of like zoom in on this. The most important functions that you could use in the Objective-C runtime are Objective-C Get class. So you can look up a class by name. Class Get instance method, which lets you look up an instance method in a class by name. And then class replace method, which lets you say essentially to the program, well, the next time you call this, go here instead. So let's take a step back and look at what we're actually trying to do. So our original goal, right, is to take Finder, which is currently looking like this, and make it look, and I'll step back, more like this. Right? We want to have our overlays, we want to have our icons, we want to have our toolbar elements. So there's a fourth step, I lied. You're going to need to figure out how Finder works, right? And that's going to be interesting. That's going to need reading assembly code. But let's take an example. So if you use Finder in the icon view mode, which is essentially the grid view that contains sort of like visually aligned, sort of like as a matrix, you have all these icons, right? That's implemented using a control that's pretty common if you've done OS X development before. Now that is based on model view controller, like most of Cocoa. So what you need to do to be able to change that is alter two different areas of the code. You want to change the model and you want to change the view. So why change the model? Well, in this case, and I guess I can explain a little bit about MVC, but in this case, the model for that view is essentially the list of files inside that folder. So why do we need to modify the model? We're not really changing what the structure of the folders is going to be on the drive. Well, we need to add a little bit of data to every entry. For every file that's in Dropbox, we want to add a little bit of data to say, what is its current syncing state? Is it currently synced or not? And that's essentially it, right? So what you do is, you first figure out where the data items for the model are created, and you add the extra state that you'll want to render. And then you change the view. So when the view is ready to be rendered, then you just check that state, and then you choose what to draw based on that state. And then on top of that, you also need to make sure that you set up some time to communicate with the client, because the Finder plugin won't itself have the information on whether a file is synced or not. It'll need to ask the client whether it can do it. And then you end up with this after many iterations. Now, that's great, but how do you know, right, what to swizzle? How do you know which function to change? And that's tricky. And to be able to figure that out, you're going to need to read assembly code. You'll need to disassemble most of Finder, figure out what these functions do, and try to replace them. You can get pretty far by relying on design patterns, right? Because since Finder is an Objective-C application written by Apple, you would expect that they would follow their own design patterns. That is mostly the case. They sometimes don't follow their own design patterns, which is hilarious, but it's mostly for performance reasons. But that's good because that can take you a large portion of the way. But that won't be enough, because you still need to know what functions Finder is actually going to call. So you'll have to do some digging, and that's where the actual reverse engineering happens. Now, the best tools for that are GDB, LLDB. Attach to Finder, start disassembling things. Start setting breakpoints randomly. See what happens. Print object is great. The Objective-C runtime lets you print objects directly to the console along with their description. Class dump is amazing. Class dump was written by a mysterious individual who essentially, what it does is you can feed it a binary, just an executable of a Cocoa application, and it will output you the header. It'll reconstruct the header for every single class inside that application. So you can get the entire object model of the application without having to code. It's also good to know what the OS X ABI, and by that I mean the binary calling conventions, are, so you can know which registers to look into to find pointers, etc. But yeah, like I said, kind of start setting breakpoints, see how things go, and rely on the Cocoa design patterns to figure out what's going on. So that mostly covers the how, but now why? Like, why would you do this? Like, why would you do such a thing and then ship it to hundreds of millions of machines? Because that can go wrong. A whole lot of things can go wrong, actually. But when done right, you can get some pretty awesome results. So I guess this is sort of like the reason why we did this. So the first thing is we really did this for the users, right? Because we think that this improves the user experience to a point where it makes it worth it. Essentially, Dropbox has always sort of focused on having polished, high-quality, user experience-driven design, and we think our obsession over detail is part of the reason why we bring value, and part of the reason why our product is so great is because it's so polished and it just works. And we think that the overlays are a good way to make sure that people actually enjoy using Dropbox as opposed to a competitor, for instance. We want our users basically to think that it just works, and then we want them to feel that they're at home. And that's why native integration is important. And that's why we wanted a consistent native look and feel. So Windows, in this rare instant, was actually superior to Mac because it has an API to do this. The Windows API is actually quite stable to do this, and it's still supported to this day. But on Mac, there was nothing. But we wanted to make sure that the experience of using Dropbox was the same thing everywhere, that there was a consistent branding and a consistent experience no matter where you're using the product. And over the years, what's interesting is that actually became a key part of our brand. We're kind of known for these little checkmark icons now. It's very much associated to our identity as a company. And finally, it's also a good chance to distinguish yourself from the competition because not everyone is willing to go this far. I don't want to, hit on Windows again, but SkyDrive, for instance, on Mac does not do this. It just looks like a plain folder. So yeah. And also, this is something that when I was an intern at Dropbox, my mentor taught me. Everything is just C code, and I'll get back to that in just a moment. So how do you get away with it? And by that I mean I don't mean how do you get away from getting sued or anything. I'm talking about how do you develop software using reverse engineered code and retain your sanity, because that can actually be fairly complicated. So yeah, we've decided to reverse engineer the world. Hooray. What now? Well, the bad news is if this were easy, everybody would be doing it, right? There's plenty of places where this could go terribly wrong. So using reverse engineering is a very powerful tool, but like any other tool, it should be used properly. So here's some of our approach, and here's what we learned over the years, and essentially the lessons we learned when we got bit. So the first thing to realize is that this is a very different class of problems. You have no documentation. The only way for you to know what a function does is to call it and see what happens, or is to try to read the code by disassembling it, right? The only thing you have is the machine code. So that really changes the game. As much as we would like to think that engineering is just about coding, documentation is actually critically important to understanding what something actually does. Because it's just really hard to convey what something does in pure code. So that means you'll be flying blind most of the time. You'll be approaching problems, and you won't really know whether something is feasible without trying it. And you don't really know when you're going to be able to get done. So that's really hard to justify to your team lead, right? It's like, I'm going to go see if this works. I'll be back in, I don't know. I don't know when I'll be back, right? It's very much a non-deterministic style of problem. And so that makes it hard to estimate, makes it hard to plan. And on top of that, the cost of everything is going to be multiplied by 10. because bugs can now come from two different sources. You can hit bugs from Apple, and that's happened to us many times, or you can hit bugs from yourself. So you have two different sources of bugs competing to essentially mess up your code. So it gets pretty interesting. So with that in mind, I guess what you have to do is ask yourself, is this really worth it? Are we actually ready to maintain this until the end of time? You need to weigh in the cost, basically. Is the user experience going to be that much better? And in our case, yeah, it was. In our case, we think it was worth it because it helped Dropbox really make its name. You also want to have a great team. I mean, not every engineer is going to be really interested in like reading assembly code all day. That's not something that every engineer loves to do. I happen to personally love to do that, but that's not necessarily what most people are interested in. And finally, you want to plan it well. You want to build a robust long-term solution. You want to make sure this is not a one-time thing. This is going to be a recurring cost, and you want to make sure that you account for that. So when you start building this, how do you build it well? How do you build it in a smart way? And how do you make sure to avoid some of the traps that we actually fell into ourselves many times? Well, first, you want to avoid a brittle solution. By that, I mean a solution that is easy to break and that stops working in almost normal situations. You want to have as little overriding code as possible here. Basically, what you want to make sure you do is if you're going to change the way some other program operates, just make sure it's using as little code as possible. Minimize the surface area. If you have less code, you have less chance that something will break it. And it also just reduces your maintenance costs over the long term. So what you want to do is do as much as you can with the least amount of code possible. It sounds obvious, but this actually helped us a lot over the years. Also, your idea of how the other program works, and we like to call this the reverse model, that should evolve over time. You should allow your understanding of the other program to grow. And what I like calling that is that it's a double moving target. So Finder over the years has changed. In fact, it was rewritten 3 times as we were using it. And so is your code. So you're essentially trying to follow code that you didn't write and can't read that is changing, and code that you wrote that is also changing. So you have 2 moving targets you're trying to follow at the same time. So that can be pretty rough. So really, the only way around this is to accept your fate and to keep digging, to find a better way to do what you're doing. Be willing to revisit your solution. The first time you find something and it works, it's probably a terrible way to do it. And you'll probably need to iterate at least a few times again before it's really in a good place. And we've done that with Finder. In fact, the version that we ship today is the 4th rewrite of the Finder integration that we proceeded to doing. So that's probably the most important thing I could say. Also, it's good to think long term. You want to be able to anticipate change. In our case, we're often asked, well, what if Apple changes Finder? What happens? Well, historically what has happened is that one of the engineers, I've been doing this since Lion, sort of is told, okay, go fix Lion and come back in a few months. That's not necessarily scalable, and it's not necessarily the right way to do it. So every time you do that, what you want to do is change your model, find something that's better, find something that will better tolerate new revisions. Now, the best way really to deal with change is to try to, if you're going to override something, if you're going to change some private code, try to change the code that's as low level as possible. You want foundational libraries. You want things that are less likely to change than Finder itself. So when we inject in Finder, we actually override not just Finder, but the library below Finder. It's called Desktop Services, and it's what Finder uses to render its content to the screen. Now that has only changed once in the past 10 years or so, whereas Finder has changed 3 to 4 times. So you want to find things that are less likely to change and more stable, because that's just better for the long term. And finally, you need to raise your quality bar. And even if you're a startup, that means you need testing, you need documentation, you need that code to be beautiful, like really, really beautiful code. Otherwise, you're just putting yourself at risk. And since you can get bugs from 2 different sources, your goal should not be to make it mostly work. Your goal should be, the only bugs I want to see in Finder are the bugs that are coming from Apple. That should be the only, that should be the goal. That's like the golden standard. Because otherwise, you get blamed, and then Apple also gets blamed for Dropbox bugs, and then Apple gets angry. and that's not something that you want to have. So being responsible about it is very important. I mean, you're basically messing with code that you can't read and that someone else wrote with the express intention of it not being messed with. So keep that in mind. Now, to conclude, really, I think the three most important points here are that it's really worth it to focus on the user experience. We got tremendous value out of this because it really helped our product. We're a very integrated product. We're almost a part of the OS in a way. So to us, that was really important. Yes, reverse engineering can be extremely powerful, but it needs to be used safely. Otherwise, you can get issues. And a great example of this is, as an intern myself, I once pushed a change to the Finder integration that I thought was brilliant, but in the end ended up crashing 10 million machines. It's like 10 million machines had their Finder just blink, right, because it crashed. Now the good part here is that Finder restarts itself, which is great, and we take care to not re-inject once Finder has crashed because of us. But essentially, yeah, it needs to be used safely. And finally, and I come back to the quote a few slides ago, nothing is impossible. Everything really is just C code. And by that I mean that this laptop essentially is only running C code. It's only running machine code. We can theoretically do anything we want to that laptop given enough time and resources, right? But that's something to keep in mind. Really, the barriers there are less, I would say, less about what's provided to you. You know, just because an API doesn't exist doesn't mean you can't do something. And this is something that I learned at Dropbox. This is something pretty important about how we approach problems. We don't like to say no. No might not be the right answer to your question, right? It might be possible to do something, and it actually probably is. So that is basically it. I would love to, take some questions. I think I'm not sure that if there's another presentation after this. I don't believe so. But if anyone would like to sort of chat about this, I'd love to meet. So if you have any questions about Finder or what we do, or other questions about Dropbox, just let me know. But I'll be around here. So, all right. Thank you.